Okay. So, that we told you that reactive powers are in the previous lecture, right, that your the reactive sources of reactive powers are synchronous generator, capacitors and reactor, right. So, other supplementary methods of improving the voltage profile on electric transmission systems are transformer load tap changers, you know that, switched capacitors, step voltage regulators and static var control equipment, right. So, that is fax devices. So, the primary means of generator reactive power control is the generator excitation. This excitation is written twice, right. Sorry, just hold on. So, this excitation actually written twice, it is here only, right. So, excitation control using automatic voltage regulator, that in short we call AVR. Little bit of AVR transfer function that we have seen in your what you call in synchronous machine modeling, right. So, the role of an AVR is to hold the terminal voltage magnitude of a synchronous generator at a specified level, right. So, the schematic diagram of a simplified AVR is shown in figure 1, this figure, right. So, this is actually V amplifier, gain is there. So, this is the voltage VR and this is the excitation system, I mean schematic diagram, and this is the synchronous generator. This 3 phase 3 terminals are there, this side is real power delta P delta Q and this is potential transformer. Then one rectifier is there, it will be rectified and or what you call and given feedback, that is a reference signal will be there, voltage reference signal, and it will be compared. And one stabilizer is there, that will see the dashed line I have shown from here, it is excited by the or what you call by the exciter voltage, right. So, the stabilizer actually is a stabilizing transformer, right, and its transfer function directly we will assume because time is short, right, but generally its transfer function it is a derivative type of thing, that is your rate feedback, that is some Sk divided by 1 plus St, something like this, right. So, this is a schematic diagram and terminal voltage here it is say Vt, right. It is I forgot to wrote it, that terminal voltage is Vt, right, and this is the change in your power delta P and delta Q, and this is a potential transformer. So, this is a typical schematic arrangement for your what you call of a, just hold on, that yours of a automatic voltage is AVR. So, this dashed line we will consider later, right, this stabilizing transformer actually we call stabilizer, we will consider later. First we will consider this one. So, an increase in the reactive power load of the generator is accompanied by a drop in the terminal voltage magnitude, this I told you, right. So, the voltage magnitude is sensed through a potential transformer on one phase, right. So, this is actually potential transformer is here, right. This voltage is rectified and compared to a DC set point signal, right, because that is why rectifier is there. The amplified error signal controls the exciter field and increases the exciter terminal voltage, right. Thus, the generator field current is increased, which result in an increase in the generated EMF. This is little bit you have studied in your machine, synchronous machine topic, right, in machines. So, the reactive power generation is increased to a new equilibrium, raising the terminal voltage to the desired value, right. We will look briefly at the simplified models of the component involved in the AVR system. So, basically our objective is that little bit of control modeling. So, the first we will see the amplifier model. The excitation system amplifier may be a magnetic amplifier, rotating amplifier or modern electronic amplifier, the last one is preferable. The amplifier is represented by a gain Ka and a time constant Ta, and the transfer function is actually Vrs upon Vs is equal to K upon 1 plus Sta, that means this one. If you go to the schematic diagram, that is Vrs upon this one Vs is equal to K upon 1 plus Sta. V is the error, right, V reference minus your this signal, if we make this signal a rectified signal, say it is Vs. So, V is nothing but the error signal V reference minus Vs, right. So, that will be represent by your what you call a first order transfer function, right. So, it is K upon 1 plus Sta. So, typical values of K, the amplifier gain, are in the range of 10 to 400. The amplifier time constant is very small actually, in the range of 0.0 to 2.1 second, and often is neglected. Sometimes we neglect this and simply we consider that it is a gain, right. So, K. Next is exciter model. So, actually this exciter modeling we will simplify it, but just see how what I have written here. There is a variety of different excitation types. If you look into that, if you see the literature, you will find that IEEE different excitation systems are given, right, recommended. However, modern excitation systems uses AC power source through solid state rectifiers such as SCR. The output voltage of the exciter is a nonlinear function of the field voltage because of the saturation effects in the magnetic circuit. This you also know, right. That is why when I was covering synchronous machine, I did not consider the nonlinearities or saturation effect, then it will take long time to discuss those things, right. I have only considered their linear part. So, thus there is no simple relationship between the terminal voltage and the field voltage of the exciter. Many models with various degrees of sophistication have been developed and are available in the IEEE recommendation publications, right. A reasonable model of a modern exciter is a linearized model, right, which takes into account the major time constants and ignores the saturations or other nonlinearities. So, in the simplest form, the transfer function of a modern exciter, it may be given as represented by a single time constant T e and a gain K e. So, VFS upon VRS, it can be written as K e upon 1 plus S T e, right. That means, if we go to the schematic diagram once again here, that is your, this is actually VF, this is VFS, this one, I am making here small, there it is capital, meaning is same. So, VF, that is your VFS upon VRS is equal to your exciter set K e upon 1 plus S T. This way represented by a first order transfer function, right. So, that is similarly when we will come to that, this is your V t. So, V t upon V f also generator side also we will see. So, that is V f s upon V r s is equal to K e upon 1 plus S t. This is exciter part. So, time constant of modern exciters are very small, right. Now, generator model for this case. So, the synchronous machine generator EMF is a function of the machine magnetization curve, and its your what you call terminal voltage is dependent on the generator load, right. In the linearized model, the transfer function relating the generator terminal voltage to its field voltage can be represented by gain k g and a time constant T g. So, it is again a first order transfer function. So, V T s upon V F s is equal to k g upon 1 plus S T g. So, this is equation 3 of all simplified thing, right. So, these constant are load dependent, k g may vary between 0.7 to 1 and T g between 1 to 2 seconds, right, from full load to no load. So, next one sensor is there. Sensor means that is your voltage is sensed through a potential transformer, right. So, and in one form it is rectified through a bridge rectifier. The sensor is modeled by a simple first order transfer function given by VSS upon VTS is equal to KR upon 1 plus STR. This is equation 4, right. So, all these component we are actually representing by first order transfer function with some gain, right. TR is very small and we may assume a range of 0.01 to 0.06 second, right. That is why here if you look into that, a simplified model of course, the time constant are very small compared to your time constant of your governor, turbine and power system, right. So, that is generator when we considering that load frequency control. That is why these two are decoupled, because when AGC action actually starts, before that the time constant is so small, their dynamic or what you call dynamics part disappear before that AGC thing starts, because time constants are very small. So, utilizing the above model result in the AVR block diagram shown in figure 2. So, this is a simplest block diagram that already this type of thing already you have studied in your third year control system engineering course, right. So, this is your K upon 1 plus STA amplifier, this is Ke upon 1 plus ST the exciter transfer function, this is Kg upon 1 plus STg which relates terminal voltage of generator field voltage, right, by first order transfer function, and this is the sensor, that potential transformer, it is sensing the voltage and rectifier, right. So, actually many studies you can find that Ta actually is equal to 0, they consider simply a Ka, and this one also Tr is very small, so they neglect Ta and Tr they neglect. So, it will be simply Ka and it should be simply Kr, right. So, a simplified automatic voltage regulator block diagram. Now, the open loop transfer function of the block diagram, the open loop transfer function of this one, this simply we can write KGSHS is equal to Ka, Ke, Kg, Kr divided by 1 plus STA, 1 plus ST, 1 plus STg into 1 plus STr. This is actually open loop transfer function, right. And the closed loop transfer function relating the generator terminal voltage VTS to the reference voltage V reference, that is VTS upon V reference actually is equal to, if you try to find out the transfer function, if you try to find out the transfer function VTS upon V reference, right, then you will get that Ka, Ke, Kg, Kr into 1 plus Str divided by 1 plus Sta into 1 plus St into 1 plus Stg into 1 plus Str plus Ka, Ke, Kg, Kr, this is equation 6, right. So, this is the transfer function. Now, or we can write VTS is equal to Ts into V reference S, that is 7. So, Ts is equal to this whole the transfer function, this Ts, the whole thing, right hand side. So, for a step input, that is V reference could be taken as 1 upon S. Using the final value theorem, the steady state response will be VTSS limit S tends to 0 S VTS, that will become K upon 1 plus Ka. So, this is actually this one actually we are taking that step response input, that Vs V reference is equal to 1 upon S, right. So, if you take V reference is equal to 1 upon S, the left hand side will become S Vt is equal to that whatever is there in the right hand side, this is equal to this one. Therefore, limit S tends to 0, right, is equal to your VTSS. So, put here everywhere S is equal to your what you call 0, right. If you put everywhere S is equal to, I mean just put S is equal to 0 everywhere. So, whatever whatever your things will come, right, that your in this expression, right. So, whatever you will get, that is your S is 0, S is 0, S is 0. So, it will be 1, right. Here also is the K, Ke, Kg, Kr, here also K, Ke, Kg, Kr. So, just hold on. Therefore, this one if you do so, that Ts is equal to V references, it will become actually it will be approximately your K upon 1 plus K, right, Vt steady state here, right. So, if you put that your V reference is equal to 1 upon S. So, actually I am making it for you that if you make S tends to 0, so this term gone, this is gone, this is gone, this is gone and this is gone. So, this is actually your Ka, then Ke, then Kg, then Kr, right, divided by your all these things S is equal to 0, 1 plus Ka, Ke, Kg, Kr, right. So, I mean it is actually K into Ke, Kj, your Ke, your what you call Ke, Ka, Ke, Kg, Kr divided by 1 plus Ka, Ke, Kg and Kr, right. For the sake of understanding, for example, if we take this K, Ke, your this approximately it is K upon 1 plus K, right. So, if you put here, that is why we are writing here that your for a step response VTS steady state will be your SVT, your what you call is equal to 1 plus k upon 1 plus k, right. So, based on this whatever we wrote, that k, k, kg, sorry, k, k, kg, kr, and this is also your k, kg, kr, right. So, now this one your what you call, if you take this example, because if you look into that in general you will find that ke, kg and kr, this is actually all are unity. That is why there we have taken ke, kg and kr is equal to 1.0, these are all 1, right. Approximately here you have taken 1, but approximately they are all are 1 1 1, right. So, in that case, that is why it is coming k upon 1 plus k, right, that is VTSS, steady state value. Now suppose this that gain Ka is unknown, Ke, Kg, Kr value all are unity, and Ta is 0.1, T is 0.4, Tg is 1 and Tr is equal to 0.05, right. So, now it is given that you have to find out that use the Routh-Hurwitz array to find the range of k for control stability. The amplifier gain is amplifier gain is set to k is equal to 10, find the steady state response. So, Routh-Hurwitz criteria, you know this, right, you know this, but little bit we will brush up our memories. So, now this is the value, all these values are substituted and k is unknown, right, but all other values are substituted in this block diagram. Now, the open loop transfer function of the AVR system shown above is that open loop transfer function k gs hs will be k upon 1 plus 0.1 s into 1 plus 0.4 s into 1 plus s into 1 plus 0.05 s, right. So, if you just simplify like this, is equal to will come 500 k upon s plus 10 into s plus 2.5 into s plus 1 into s plus 20, right. Or if you multiply all, this will be 500 k divided by s to the power 4 plus 33.5 s cube plus 307.5 s square plus 775 s plus 500, right. So, now characteristic equation you know that is given by 1 plus k gs hs is equal to 0. Therefore, this is the characteristic equation 1 plus 500 ka divided by s to the power 4 plus 33.5 s cube plus 307.5 s square plus 775 s plus 500 is equal to 0. Now, after getting this characteristic equation, we will go to Routh-Hurwitz criteria. So, before that, before directly going to that, let us brush up our memories regarding Routh-Hurwitz criteria, right. So, the Routh-Hurwitz stability criteria, then we will go to the problem. So, the Routh-Hurwitz criterion, you have studied in your third year control system engineering. So, very simple thing, provide a quick method for determining absolute stability that can be applied to an nth order characteristic equation of the form. Suppose your characteristic equation is a n s to the power n plus a n minus 1 s to the power n minus 1 plus a 1 s plus a 0 is equal to 0. This is my characteristic equation, it is nth order polynomial, right. So, the criterion is applied through the use of a Routh table defined as that s to the power n. So, this is a n, then your this will be a n minus 2, a n minus 4 and so on, right. Similarly, for s n minus 1 it will be a n minus 1, a n minus 3, a n minus 5, right. So, a s n and these two you written. So, s n minus 2, that will be your what you call that your b 1. So, b 1 you know that it will be a n minus 1, you know that row. Just I have written at the bottom, a b 1 will be a n minus 1 into a n minus 2 minus a n into a n minus 3 divided by your what you call that your a n minus your what you call 1, right. So, that means that b 1, b 2, b 3, c 1, c 2, c 3. Now, your what you call that a n is equal to your a n minus 1, a 0 are the coefficient and of the characteristic equation, and b 1 you know this, I told you that it is a n minus 1 your into a n minus 2 minus a n minus 3 divided by a n minus 1. So, this is my b 1. Similarly, b 2 will be also from this equation, you know that from this equation b 2 will be your n minus 1 n minus 4 minus n into n minus 5 divided by n minus 1 etc. right. This way computation will go. Similarly, for the fourth row, that is your C1 C2 also similar way you have to compute. So, C1 will be B1 a minus n minus 3, the C1 will be B1 n minus 3 minus B2 n minus 1 divided by B1, right. So, similarly, your C1 will be B1 n minus 3 minus B2 n minus 1 divided by B1. C2 is equal to B1 n minus 5 minus n minus 1 B3 upon B1 etc. right. This way computation, this you know. Now, calculations in each row are constant are continued sorry until only 0 elements remain, right. The necessary and sufficient condition that all roots of characteristic equation lie in the left half of the S plane is that elements are that I mean if system will be stable if all the roots real part of the roots all the roots lie on the left half of the S plane, that is your real part should be negative, right. So, that elements of the first column of the Routh-Hurwitz array have the same sign, right. If there are changes of signs in the element that you know of the first column, the number of sign changes indicates the number of roots with positive real parts, right. This you know. If the first element in a row is 0, right. So, it is replaced by a very small positive number say epsilon, and the calculations of the your calculation of the array is completed, right. If all elements in a row are 0, the system has poles on the imaginary axis, that you know. Pairs of complex conjugate roots forming symmetry about the origin of the S plane or pairs of real roots with opposite sign. So, in this case an auxiliary equation is formed, right. So, if it happens so, an auxiliary equation is formed from the preceding row. All 0 row is then replaced with coefficient obtained by differentiating the auxiliary equations. So, all these things you have what you call that you have studied in your third year control system engineering. Now, if we go to Routh-Hurwitz array, therefore, now we are coming which results in the characteristic polynomial equation. So, in that case it will be s to the power 4 plus 33.5 s cube plus 307.5 s square plus 775 s plus 500 plus 500 k is equal to 0. Now, Routh-Hurwitz array for this polynomial is then make it is S4, coefficient is what, then it is S square 307.5 and s to the power 0. So, 500 plus 500 k, right. Similarly, S cube this one also 33.5, 775 and 0.0. Now, B1, B2, B1 is 280, if you similarly if you compute it will be 284.365 and B2 will be 500 plus 500 k, B3 will be 0. Here one sign mistake I have made it, I am correcting it, actually this should be plus, this should be minus, right. That means, this should have been actually 716.1 minus 58.9 k, right. After scanning this, it came to my mind that it was when I am writing it by mistake I made this one, it will be 716.1 minus your 58.9 k, right. So, if you now this is your corrected, right. So, it will be plus 716 and minus 58.9 k. Now, if it is plus, if it is minus, this or what you call that you have to make all these elements is positive, but this one if you make positive the all the rows, right. For example, that will be 500 plus 500 k, it will be greater than 0, it has to be positive. That means, your k a, right, greater than minus 1, this is one condition, right. Similarly, this one your what you call that your 716.1, this is plus actually minus 58.9 k, that has to be greater than 0, right. That means, your if I make it like this the other way, that 58.9 k less than actually 716.1. That means, if you simplify that k will be less than 12.6, right. That means, that this k value for stability it will like -1, k greater than -1, you are less than 12.6, but k a not is equal to 0, right. If k is equal to 0, then whole system that your nothing will happen, right. So, if we do so, then from the S1 row we see that for control system stability k must be less than 12.16. It is not 12.6, it was actually k actually less than 12.16, not 12.6, right. So, also from this S0 row k must be greater than -1, thus with positive this thing value of k for control system stability, the amplifier gain must be k less than this thing, but here also I can add this one, that your -1, your k greater than -1 less than 12.16, this is 12.16, I by mistake I have written 6, it is 12.16, right. So, it will be, but at the same time k not is equal to 0, right. So, for k is equal to 12.6, right, it is just check, it seems 12.16, just check it, right. If many places I have written 12.6, perhaps it is 12.16, I do not have calculator here to calculate, right, otherwise I should have corrected here, but just take it, nothing, it is nothing actually. So, this row, if you look into this row, it will be 284.365 s square plus 6580 is equal to 0. I mean s will become plus minus j 4.81, right. Then the roots are lying on the imaginary axis. This, that is for k is equal to, just check again I have written 12.6, just check whether it is 16 or 12.6, right, just check, I do not have calculator here. So, we have a pair of conjugate poles on the j omega axis and the control system is your marginally stable, right. So, this is the thing. So, the closed loop transfer function of the system, that is your figure I have given page number R10, right. So, the same figure, same block diagram, if you find out that VTS upon V references 25 k s plus 20 upon all these terms, right. So, at steady state V reference is equal to your 1 upon s step input, V reference is equal to 1 upon s the step input. So, if you find out VTS as limit s tends to 0 s VTS, it will become 1 k upon 1 plus k, right, and it is given that for k is equal to 10, what is the steady state value. So, for k is equal to 10, it will be 10 upon 1 plus 10. So, 0.909, right, that is steady state VTS, and the steady state error will be, because it is 1 per unit was the voltage. So, 1 minus 0.909, so 0.091. So, steady state error is quite high, right. So, that is the thing, only thing is that this k value in the previous example, you just check whether it is 12.6 or 12.16, or next video lecture I will rectify that one, right. So, otherwise everything is okay, I do hope that all calculations are correct, right. So, thank you very much, we will back again.